All right. Let's continue. Okay, now I want to introduce the last section of this chapter, which is about gauge fields. So again, let's start what we had classically. Classically, we have electric field, E, and magnetic field, B, and these are the physical objects. But what we do in electrodynamics, if you are taking that course, when we calculate things, it's easier to calculate things in terms of not these physical fields, but so-called gauge fields. And gauge fields, there are two of them. There's like scalar potential, which is phi, and vector potential, which is A. Okay? So these things, they depend on x, y, z, and t, but let me not write it, right? I have to write a lot of things. So this is also x, y, z, and t. In the most general sense, they depend on all coordinates and time. And once you write this phi and a, scalar and vector potential, you can obtain physical fields in terms of these, right? Electric fields, how do I write electric field in terms of this? Does anybody know? E, suppose they will only have like scalar potential, anybody? Gradient, right? So this is minus gradient phi. What if I also have vector potential? Anything to change here? What's that? Yes, thank you. So this is del A, del T, and B is a little bit simpler. B is curl of A, right? Once you have A and phi, you can obtain physical fields. And in the following for calculations, I want to use summation convention to write these things a little bit more effectively. I think I heard Einstein said his biggest contribution to physics is summation convention. I sometimes agree with that. So for that, I'm going to use this notation. So EI, ith component of electric field is going to be minus del I phi, right? Minus del T, ith component of vector potential, and this one B, ith component of magnetic field. For curl, we are going to use this epsilon ijk, which we talked about it last time. Epsilon ijk del J AK. And if you have never seen this, don't be scared. This actually makes life much easier if you know how to deal with this. And now I want to write a Lagrangian, right? What is the Lagrangian? Okay, what is the Lagrangian for a charge Q in electric and magnetic fields? So Lagrangian depends on x and derivative of x, and we need to do y and z similarly. And here's the Lagrangian. I'll write and I'll argue why it is like this. So this is 1 over 2 m v squared plus q v dot a minus q times phi. Again, this a and phi are x, y, z, t dependent. And here I want to use v to be dx dt. Or if I want to use the summation convention, this is going to be 1/2 m vi squared plus q vi ai minus q phi. Good? Like these repeated indices are summed over. There's also repeated index here because it's like square. And we write Lagrangian because sometimes it's harder to work with Newton's laws, right? F is equal to ma, and from the Lagrangian we can, for example, produce the equation of motion, and this is what we call Euler-Lagrange equation, which is, if you want, a generalized form of Newton's laws. And this one goes like del L del xi minus d dt del L del xi dot is equal to 0. Now let's calculate this equation of motion and look at it. And if it gives something meaningful to us, we are going to say, okay, this is like a good Lagrangian. So what I will do is I'll calculate this, and I'll set up this equation and look at it, what it means. So del Lagrangian del xi is equal to, right? So what we are assuming is xi and its derivative are independent variables. That's why I write this, right? X and its time derivative are independent. So that's why there is no derivative coming from here. There is no derivative coming from here, but there is this q vi. Let me also shorten the notation, like del xi is del I acting on, actually I need to use a different index. So this is j, this is I, so this is j, this is I, right? Now I take the derivative of this term minus q del j, derivative of this term, phi. And the second one is I need to take derivatives with respect to dot. And in this case I'm going to produce this. So this is going to be m 2 vi del xi dot del xj dot. What is this? Like something like del ui del uj, right? 0 unless I and j are equal, right? That's why this is going to be 2 vj, and I can get rid of this. And this second piece, I also have exactly the same thing here. This is going to be plus q. If you take the derivative with respect to vj, which is x dot, this is going to be aj. Yes? These two lines? Oh, yes. I think there's like 1/2 and there's 2. Yes, absolutely. Thank you. Good. Now I'm going to take total, right? This is like this is the place that we need to be careful about total derivative versus partial derivative. One of the few places we need to be careful. So this is the total derivative of this thing. So this is d dt. The first term is easy. M, derivative of velocity is acceleration. So this is, I'm going to write it aj. But now here, right, this thing aj depends on x, y, z, and t. Right? And I'm going to take derivative with respect to this thing. I need to use chain rule for this. So, and this thing q, the way I write this is like I can take full time dependence, or I can have del aj del x I del xi del t. Right? I just didn't do anything. I just used the chain rule. And what is xi xt? This is the velocity, so I'm just going to write it like vi. Now let's put all of these in the Euler-Lagrange and see what it looks like. So here, right hand side is this. And I'm going to write this as 0 on the other side. So this is time derivative is this. And left hand side is this. Okay, now we need to play with this just a little bit. So I want to leave m aj is equal to. So I have this term minus q del j phi, and I'll combine this term with this term. Actually, let me also put this time derivative to here, minus q del aj del t. So this is the first term. So I got rid of this, I have two more, and it will be plus q vi del j ai minus vi, this one, del I aj. So this first term is already nice, right? This is minus q, or like q times minus del phi, right? So this is, how do I write it? So this is minus q del phi, q minus del phi minus del t a jth component. So I already have electric field in my equation of motion. That's good. Now there is this also second term. Let's see what it looks like. And for that, I want to consider the following. Let's consider V. Let me use a different color. V cross B, and I want to look at jth component of this thing. And I will use this epsilon j. Let me use ik is equal to vi bk, and for bk I'm going to use this del cross a kth component. So this is going to be epsilon k l m del l a k. So let's combine, and I can cycle this. So this is, as you can see, this I, J, I, K, and epsilon, like K, L, M, they only have M common, K common. I want to cycle this to the beginning. So this is epsilon K, J, I, epsilon K, L, M, VI. So I got VI del L, A, K. And does anybody know what this product of two Levi-Civitas give? And I think this is, yeah, there are two deltas, so this thing is going to give, so you do the following. So you either pair, right? Once you have a common index, you look at the indices which are not common, and you are saying they should also be common. Otherwise, right, these Levi-Civitas are going to be 0. So you either pair it like this, J with L and I with M, or you pair with J with M, I with L. So this is going to give you delta J L delta I M minus delta J M delta I L. Delta J L I M minus J M I L. Good. Now I can write what this thing is equal to. So V I L in the first term is equal to J del J, and K in the first term, okay, where did, oh, I think K is K. So let's, what did I do here? So I, J, I, so what did I do here?
In the cross product, shouldn't AK be AM?
So this one?
I'm not sure, but...
sorry. This is, so this is K, and this is K, L, M, and I put them together, so this is I, L, K, So if I take Vi, L is J, and K is K. So Vi, so something is not adding up here.
Just for VK, should there be AM instead of AK? Because it's the K.
Oh, yes, thank you. So, right, I messed up here. Absolutely, yes, thank you. So this is, so K, L, M, L, so this is M. Okay, this is M. But this is the nice thing about this notation. If something doesn't make sense, indices don't match, and you know you are doing something wrong. Now I think I can fix that. So this is M is equal to I minus, again this is Vi. So here L is equal to I, del I, and here M is equal to J, A, J. Let me check. So this is IJ, IJ, I, and IJ. And I look at this. So this line is exactly this line, right? So this is IJ, IJ, I, and IJ. Therefore, this term is equal to this term. So let's write this. Then M times A, J is equal to Q times E, J, right? This is Jth component of electric fields. And I have plus Q V cross B Jth component. And what is this equation? This is the Lorentz force, right? This is Lorentz force. And since I reproduced the classically correct equation of motion, right? This is the correct equation of motion for a particle in electric and magnetic field. My Lagrangian is correct, right? That's all I need from my Lagrangian. As long as using this Lagrangian and Euler Lagrange equation, if I produce the equation of motion, that's a good Lagrangian. Nobody can say anything to you as long as this happens. Okay, so the first step is done. The second step is to obtain Hamiltonian. Why do we want to obtain Hamiltonian? Because quantum mechanics is formulated in terms of Hamiltonian. And the idea is Lagrangian is a functional of xj and time derivative of xj, and Hamiltonian is so-called Legendre transformation of Lagrangian. Hamiltonian is going to be a function of xj and pj, which is, okay, let me write in a new line, so which is equal to, this is the Legendre transformation, xj dot pj minus L, and this pj is defined as pj is equal to del Lagrangian del xj dot. So let's calculate this pj. Pj is equal to, so this is what I just, okay, let me write it, del Lagrangian del xj dot, and our Lagrangian is here. If you take the derivative with respect to xj dot, you are going to have m vj plus, there's another one, q times aj. So this is m vj plus q times aj. Therefore, whenever I see m vj, I can write it as pj minus q aj. So this p, so this p is sometimes called canonical momentum, and this mv, which is the time derivative of position, is sometimes called mechanical momentum. The one is mechanical momentum, The other one is canonical momentum. And we are going to see mechanical momentum has nicer properties. We'll see it maybe tomorrow. We may not have time today. Now, our program is what? We calculated Pj and put it here and calculate the Hamiltonian. Now, Hamiltonian is equal to, so xj dot Pj minus Lagrangian, and this is equal to Vj, and Pj is we just calculated here. Okay, let me write it like this, minus, and Lagrangian is 1/2 m Vj squared plus q Vj Aj minus q phi. Q multiplying Aj. So this is the charge. This is the external, the charge of the particle. A is the vector potential, and you multiply Q with A, and it is kind of like a momentum.
It's momentum of what?
So it's the so this entire thing is the momentum, mechanical momentum of charged particle in an electromagnetic field. So when you have particle in free space, its momentum is just simple momentum p. But when you have like electromagnetic fields, you have this contribution. And at the moment, it just comes out of equation. That's all I want you to see at the moment. But I'll show you later how this thing actually shows itself physically, especially in quantum mechanics. It's like very important. At the moment, everything you need to know is here, right? P is generalized momenta and defined by derivative of Lagrangian like this, and it gave us this. From here, I just solved this mvj, and I found this. 2 lines of calculation. And now I want to just simplify this thing. So this is Vj. You can see I have this Pj minus Qaj minus 1/2 m Vj squared plus Q phi. And I want to write this Vj. Whenever I see mVj, I want to write this thing. And this is going to give me, so I have one Vj here, so this is going to be 1 over m Pj minus Q Aj times this squared minus 1 over 2m, right? I write it like m squared. Now m squared Vj is square of this, Pj minus Q Aj squared plus Q phi. And you can see this term and this term are the same. At the end I have 1 over 2m Pj minus Q Aj squared plus Q phi. And this is my Hamiltonian. Let me write it in the final form. H in an electromagnetic field is going to be this P minus Q A squared divided by 2m plus Q times phi. So this is the Hamiltonian for a charged particle in gauge field. And gauge field is A and phi. And this prescription, like writing Hamiltonian like this with shifting P, is called minimal coupling. Why did, I don't know. I mean, it is just what it is called. So this is minimal coupling. Or sometimes minimal coupling scheme. Now, once I have the Hamiltonian, I can go to quantum mechanics, right? Quantum mechanics is I, h bar, del psi, del t. Just write the Schrödinger equation with this Hamiltonian. And that's it, right? And the reason I like this is like this is where almost everything you learned converges, right? So we have been teaching you like classical mechanics and electromagnetic theory, quantum mechanics, and they all come together to derive this result, right? You have to know all of them, and not that you have to know crazy calculations, just basic definitions, and that's all we need. So I want to show one last thing and I will finish it. And this, unfortunately, is the most important thing about this calculation. I want to show something called gauge invariance or gauge transformations. So we know, right, this phi and A, these gauge fields are not physical. And physical fields are E and B. And if you do, for example, phi goes to something like phi minus del lambda del t for any lambda x, y, z, t. I'm not going to write the argument. And A goes to A plus gradient of phi. E and B fields do not change. Why? Let's write. So E is minus del phi minus del A del t, and this is going to give us, right, after the transformation, this is going to go to minus del phi minus del lambda del t, and I need to take time derivative of A, so this is going to be minus del A del t. Something is not right. I think this is minus, this is plus. Oh, this is minus minus, this one is plus, right? There is like one minus here, this is plus. And this is del A del t minus del t, this term. And you can see like these derivatives, they always commute, so this one is going to cancel this one, and this is going to give us the physical field. The physical field is unchanged after this gauge transformation. Let me also do this with the B field. Is curl of A, and this is going to curl A goes to A plus gradient of this lambda, but we know curl of gradient is always 0, right? So this thing acting on here is going to give us 0. This is del cross A, and this is B. So E field and B field are unchanged after this transformation. Sometimes we say E and B are gauge invariant. And the key part is how does psi change, right? Psi is not observable, so we don't expect psi to be invariant under gauge fields. So let's see, like this is the Schrödinger equation. And my claim is, in addition to these two transformations, we also need to put psi should go to psi times e to the I over h bar q lambda. Okay, that's my claim. I'll show this, and that will be the last thing I do today. Good. Let me actually call these phi prime. Let me call this. This is psi prime. This is phi prime, and this is going to be a prime. So this is the Schrödinger equation without the primes. Let's call this gauge choice number 1, and the second gauge choice, like with the primes, is going to be psi prime here, a prime here, phi prime here, and psi prime. And the question is, so this is gauge number 2, and the question is, how can we be sure that gauge choice number 1 is consistent with gauge choice number 2? So that's what I want to show in the next few minutes. The question is, are these two equations compatible? If not, we are in trouble, because it means that Schrödinger equation depends on gauge choice. That means it's not a physical equation, and we have to make sure these two things are compatible with each other. So let me take this equation number 2 and rearrange it just a little bit. So I want to take this equation and I want to rearrange it in such a way that I want to make calculations a little easier. So let me take this q times phi prime on this side. So this is, so I'm going to write, so this is minus q phi prime. So this entire thing acting on psi. Now this is taken care. I will erase this, and this thing is going to be like that. Good. And this is also good. So let me call left hand side 1 and right hand side 2, and let's calculate left hand side and right hand side separately. So first, left hand side, so it is this object. I think this is also prime, so this, I want to start with this, and this is equal to I h bar del t minus q phi, and phi prime is equal to phi minus del lambda. Phi prime is equal to phi primes del lambda del t. So and then this is going to be equal to plus q del lambda del t, and psi prime is going to be equal to psi times e to the I over h bar q lambda. This is psi times e to the I over h bar q lambda. Now let me separate this. So this is I h bar del t and the second term I want to write it as minus q phi plus q del lambda del t acting on this thing. And here, so this derivative can act on psi or can act on this phase factor, because there is x, y, z, and t dependence on this lambda function. So let's open that up. So this piece is I h bar del psi del t times e to the I over h bar q lambda, or plus I h bar psi e to the I over h bar q lambda I over h bar q lambda del q del lambda del t. So this h bar is going to cancel this h bar. I times I is minus 1, so this is minus, and you can see this is, let's write this, so this is equal to I h bar. I want to write this phase in front, so e to the I over h bar. Well, let's write it, e to the I over h bar q lambda del psi del t minus e to the I over h bar q lambda times q del lambda del t psi, and this piece minus q phi psi e to the I over h bar q lambda plus q del lambda del t psi e to the I over h bar q lambda. Now we see this vector is going to cancel this, and at the end what we are going to have is e to the I over h bar q lambda, and I think I forgot I h bar here, so this is I h bar del t, and this vector minus q phi acting on psi. Good. So I calculated the first term, the left hand side. Now I want to calculate the right hand side. So this is to the right hand side. But for doing that, I want to consider the following. So P minus Q A prime acting on psi prime. So that's what I have here, and I'm only taking the first vector, and I will apply this quantity in the parentheses one more time in just a little bit. So this is going to be equal to minus I h bar, so this is the momentum, minus q a, so this is a, and I also need to have the second piece for a prime, which is this gradient. So this is minus q gradient of lambda, and this entire thing is acting on psi, and psi prime, and psi prime is equal to psi times e to the I over h bar q lambda. And similarly, so this gradient can act on psi, or it can act on the phase, and it's going to produce two vectors. So let's get those. First, I can have P acting on psi times e to the I over h bar q lambda, or it can jump over psi and act on this. So this is psi e to the I over h bar q lambda, and this minus I h bar, and I have I over h bar q and gradient of lambda, and these other factors minus q a minus q gradient of lambda. So this h bar is going to cancel this h bar, minus I times I is plus, and I have here, okay, let's like this psi e to the I times q. Okay, I think here I forgot, so there's also here this entire thing is going to be multiplied with psi prime. So let me write it like this. So this is plus psi e to the I over h bar q lambda, and now I can see this vector. This is q gradient lambda, this is minus q gradient lambda, so this vector is going to cancel this vector, and what remains I'm going to combine like this. So this is going to be, I want to again write this e to the I over h bar q lambda. So this is p minus q a acting on psi. Good. So now I have one factor. And we can see here, so if we were to act this p on psi prime, it's going to give us e to the I over h bar q lambda p plus q gradient lambda times psi. Whereas if we apply p minus q a prime to psi prime, so this is the mechanical momenta in the primed gauge choice. So this is going to be equal to e to the I over h bar q lambda p minus q a times psi. So what we see here, so the canonical momenta is not gauge, the jargon is it's not gauge covariant. So this one, whereas this one you can see this is like there is like p minus qa, p minus qa, whereas mechanical momenta is gauge covariant. So this is the good object to work with for this reason. Now let's consider applying a second power, but before applying a second power we can see the pattern, right? So if this p minus q a prime is acting on something like psi times e to the I form, so it jumps over e to the I form and produces this form and it becomes psi, right? Now I want to do the same thing one more time. So we now want to calculate p minus q a prime. So this entire thing is acting one more time, so it's going to be like this. So what I mean is whenever this object jumps over this exponential, there is going to be like a shift in p, and that's all we need to know, right? So then and that's where we saw this. I want to do exactly the same thing. So this is going to be equal to, so this is e to the I over h bar q lambda. Now I jump over this, then p is going to be p, I just saw it here, right? P is going to be p plus q gradient lambda. So this is p plus q gradient lambda. And now I need to open this up to, so this is q a minus q gradient lambda. So I remind you, so this piece is minus q a prime, and what remains here, it's going to be, so this vector p minus q a and psi. Similarly, this plus q gradient of lambda and minus q gradient of lambda cancel, and at the end what I have here is e to the I over h bar q lambda p minus QA squared acting on psi. Therefore, what we see is this 2 is going to be equal to 1 over 2m times this thing. Now let's combine 1 and 2 and see what it looks like. So combine 1 and 2. From 1, what we obtained was here. So this is 1. Is equal to, from 2 we obtain this piece. And you can see these phase factors did their jobs. You can say thank you and cancel them. And now I want to move this q times phi on the other side. And with this becomes I h bar. Okay, this is del t. Del psi del t is equal to 1 over 2m p minus qa squared plus q phi psi. And we look at this equation, and what we see is, so you can see this is exactly the Schrödinger equation in the gauge choice number 1. Therefore, what we have shown is these two gauge choices are compatible. Thus, gauge choice number 2 implies gauge choice number 1, right? These two gauge choices, like Schrödinger equation written in these two gauge choices, are consistent with each other, and the technical jargon to say this is that Schrödinger equation is gauge covariant. Okay. All right, that's it for today. Thank you.